Okay, we go to topic 24, medical physics. Under medical physics, production of and use of ultrasound. 24.2, production and use of X-ray. This one is a new one. 24.3, PET scanning. Okay, let's look at production and use of ultrasound in diagnosis. Right, there's a syllabus. This is the only part that is new. Previously, they didn't mention it. They give it in the data sheet. So this one is also in the data sheet. Okay, you go over that. Right, speed of light is important under medical physics also. And then you can remember radioactivity exponential is very important in ultrasound and X-ray. Okay. Intensity reflection coefficient given, so you know where to find it. Okay, we'll introduce acoustic impedance attenuation, principle of generation and detection, used to obtain diagnostic info. Right. Part one, we look at what is ultrasound, piezoelectric effect, production of ultrasound, transmission and absorption of ultrasound in the medium. Then part two is ultrasound for diagnostic. Don't bother about all that. Right. This is an image of opening the blood-brain barrier. Right. The image of ultrasound. Ultrasound is a type of imaging. We use high-frequency sound waves to look at organs and structures inside the body. Healthcare professionals use it to view the heart, blood vessel, kidney, liver, and other organs. During pregnancy, doctors use ultrasound to view the fetus. Unlike X-ray, ultrasound does not expose you to radiation. So in a sense, according to our knowledge, it's quite safe. No ionizing radiation. So not exposed to unnecessary health hazard. Ultrasound scan of human kidney. Right? There's a kidney there. Okay, review. Ultrasound are longitudinal waves. They are pressure waves. The intensity of wave is proportional to the amplitude square and inversely proportional to the distance square from source. The speed of wave changes as it enters medium. As the wave enters a medium, part is reflected. That's the incident ray, incident angle. Part is reflected. There's the angle of reflection. Same, that's the angle of incident. And part is transmitted. Transmitted means it enter the boundary That is the boundary. Right? This is also called transmitted but we are more interested in this one. Go inside enter the boundary That enters the medium, and in the medium, part of it is transmitted and part is absorbed. Right? So that part, the reflected part is transmitted. At the same time, this one is absorbed inside the medium. Okay, ultrasound. Let's look at the range. Where is ultrasound? Subsonic, acoustic, 20 hertz to 20 kilohertz is acoustic. Ultrasound is above 20 kilohertz. Animals and chemistry. We use ultrasound here. So 1 to 10 megahertz, diagnostic purposes. We use it for diagnostic purposes. Audio range, That means we can hear the sound is 20 to 20,000 hertz. Sound above 20 kilohertz, 20 kilohertz is called ultrasound. Human tissue, the speed of ultrasound is 1,500 meters per second. Wavelength of 2 megahertz. You consider that speed there. It's about 1 millimeter lah. Okay, or 0.075 millimeter, right? Close to 1 lah. Ultrasound. Range of frequency used is 1 to 10 megahertz. Frequency range represent a compromise between lower frequency, which would diffract, right? Diffract and spread out too much, and high frequency, which will be absorbed too easily by tissue. The higher the frequency, remember, the smaller the wavelength, and hence the greater detail of the image. This one summarized for you in picture form. 1 megahertz, diffract and spread out too much. That's a formula we will use quite frequently under modern physics and medical physics. Then be absorbed too easily by tissue, 10 megahertz. And 10 megahertz is smaller the wavelength, greater detail of the image. Right? These are application. Don't want to study, don't study, just for your info only, extra knowledge only. Bats use ultrasound to navigate in darkness. Dog whistle, a whistle which emits sound in ultrasound range, used to train dogs and other animals. Ultrasound imaging or sonography is used in medicine, used to detect invisible flaws. Industry, ultrasound is used for cleaning, mixing, and accelerating chemical processes. Animals such as bats and porpoises use ultrasound for locating prey and optical. Producing sound. When an alternating, right, the key is there must be something that's changing now. Alternating voltage of audio frequency is sent to a loudspeaker. There's a loudspeaker. The vibration of the diaphragm, right? Diaphragm is in the loudspeaker, produces the sound wave in air. Right? Same, we will have a gadget there, transducer, to produce the ultrasound. Piezoelectric effect. Certain crystal, example quartz, when unstressed, the centers of charge are positive and negative ions bound in the lattice of the piezoelectric crystal coincide. There's no PD. Right? Crystal, example quartz, when it's unstressed, there's no PD across it. When pressure is applied to the crystal, for example, you apply attention there, the crystal distorts and the centers of charge for the positive and negative ions will no longer coincide. When stretched, the PD appear across the crystal. Right? Depend on tension or compression, the PD polarity also changes. Okay, you can see that under tension or compression, PD is different. When the crystal is compressed, the PD across the crystal reverses. Magnitude of voltage Magnitude of voltage generated depends on magnitude of pressure applied to the crystal. Polarity of the voltage depends on whether the crystal is compressed or expanded. Increase or decrease in applied pressure. This one memorize. What is piezoelectric effect? The voltage will be generated across the quartz crystal when a pressure is applied to the crystal. The polarity depends on whether the crystal is compressed or stretched. That's all. Right? Memorize it. Piezoelectric effect. What is it? Principle of generation of ultrasound waves. Quartz has a complex structure. Right? That's the structure of the quartz crystal, quartz molecule. Right? That's silicon positive ion. This two dimension, silicon positive ion. And then at the pore side, these are oxygen. So there is a center of gravity, 1/3 of the height. This is just for your info only. I don't think they will bother to ask you all this. Piezoelectric crystal example quartz have a complex ionic structure. Oxygen ion. When crystal is unstressed, the center of charge of the positive and negative ion bound in the lattice of the piezoelectric crystal coincide. Right? This is unstressed. Two sides of the crystal are coated with a thin layer of silver to act as electrical contact. Okay? There's your electrode to act as electrical contact. There's your quartz crystal. Thin layers of silver. Right? When it's unstressed, if a constant voltage is then applied across the electrode, that is across a layer of silver, the positive ions are attracted towards the cathode and the negative oxygen ion towards the anode. Right? So it becomes thinner or thicker, depends on the polarity. This causes distortion of the silicate ions depending on polarity of the applied voltage. The crystal either become thinner or thicker as a result of the altered charge distortion. Applying alternating voltage. Right? We are using what we have learned about oscillation, resonance. And alternating voltage applied across the silver electrode will set up mechanical vibration. So that alternating voltage is like this person pushing. Right? And alternating voltage applied across the silver electrode will set up mechanical vibration in the crystal. If the frequency of the applied voltage is the same as the natural frequency or vibration of the crystal, resonance occur and the oscillations have maximum amplitude. Sound wave at the same frequency as the alternating voltage. Alternating PD is created in the surrounding medium. Same idea as resonance in the open, enclosed pipe and open pipe. Choice of crystal, dimension of crystal can be such that the oscillations are in the ultrasound region, ultrasonic range, thus producing ultrasonic waves in the surrounding medium. Thickness of this determines the resonant frequency on the same principle as resonant impact. We don't need to go into more detail. Explain the main principle behind the generation of ultrasound to obtain diagnostic information about internal body structure. Memorize this. Opposite phase of quartz or piezoelectric crystal are coated with silver to act as electrode. When potential difference is applied across crystal, the centers of positive and negative ions of silicate are not coincident. This causes crystal to change shape. Alternating voltage in ultrasound range is applied across a crystal. It causes crystal to oscillate. The crystal is cut so that it vibrates in at resonant frequency. Right? The frequency that we want, we choose the size of the crystal. What's a transducer? Any idea what is a transducer?
Oh, no.
It's a device, any device that converts energy from one form to another. Right? Convert energy from one form to another. There's your ultrasound transducer and receiver. A simplified diagram of a typical piezoelectric transducer or receiver. That's how it looks like. The size involved. Such device operate in a megahertz frequency range up to a maximum of 600 megahertz. That is your piezoelectric crystal, this one. Coated on the surface will be the silver electrodes. There's your coaxial cable. Take the alternating voltage out of it, or send the alternating voltage inside. There's your earth metal case. Backing material. Absorber block. Behind the disc prevents ultrasonic. Right? That's your backing material. That one. Behind the crystal prevents ultrasonic wave created at the two surfaces of the disc cancelling each other. Okay. Transducer and receiver. Ultrasonic transducer can also be used as a receiver. Transmission and absorption of ultrasound in a medium. Right? Medium 1 is here on top. Medium 2 is the bottom. That line is the boundary between the two medium. The relative magnitude of reflected and transmitted intensity depends on the angle of incident. Then the angle of incident, that's the angle of incident. And the two media themselves. In these two mediums. So we use conservation energy. I is the incident intensity of the wave. IR is the reflected intensity. This is the transmitted intensity. Right? Transmitted means it enter the second medium. What does IR and IT depends on? That's what we are going to study. Okay, we define new terms. Relative intense magnitude of IR and IT are quantified by reference to specific acoustic impedance. Acoustic impedance, symbol Z of material, is defined as product of density and speed. In terms of formula, right? Speed of wave, density of medium. right? Memorize it. Unit density is kilogram meter minus 3. Speed is meter s minus 1. Kilogram meter minus 2 s minus 1. Usually the unit will be given you lah, because there's no point in testing you already. AS already tested you. But sometimes they may ask you lah, right? What's the unit lah? But very rare lah. Acoustic impedance important in determining the acoustic transmission and reflection at the boundary of two material having different acoustic impedance. Okay, there is the substance. First column is the substance. That's the density of the substance. That's the speed of ultrasound in the substance. That's the acoustic impedance. Speed of ultrasound is large in bone and air. And speed, the ultrasound is larger in bone. Bone is very high, 4,000. Air is very small compared to water and body tissue. Z is largest in air. Sorry, Z is smallest in air. That's your Z. Smallest in air and largest in the bone. For water, soft tissue, fat, and muscle, they are almost quite similar. Almost quite similar. As approximately the same Z. Right? Refraction and transmission coefficient. Right? That's a medium one. Usually it's air. You have to enter. And medium 2, Z2. Right? Z is the acoustic impedance. And there's a boundary between the two medium. So there's a incident intensity I. Enter is a transmitted intensity IT. Right? Depend on the medium or the boundary. And then there's the reflected intensity. That's a conservation of energy formula. Z acoustic impedance of the medium. The intensity reflection coefficient alpha, ratio of reflected intensity to incident intensity. Okay? Reflected intensity, incident intensity. How do you calculate the reflected intensity? Z2 minus Z1 square is always positive lah. Whether Z1 minus Z2, it doesn't matter lah, because it will always be positive. And this one, you add them up. The top one is subtract, the bottom one is add them up. Fraction reflected, right? That's the fraction reflected. The percentage transmitted will be this fraction reflected 1 minus alpha times 100%, because this is fraction. Right? Stop me if you got any question to ask. Right? So this alpha allows us to determine IR, right? How much of the intensity is reflected back. Remember, we want it to enter. Then we can know what happened to medium 2. Right? If all of it is reflected, it's no use. specific acoustic impedance. If Z1 and Z2 are nearly equal, alpha is nearly equal to, right? These two are almost equal, then alpha is almost zero. Right? So when you subtract, it's almost zero. Very little reflection, mostly transmitted. Example, gel and skin. So usually when we send ultrasound into the body, we put a gel, right, which has the same Z as the skin. If Z1 is very much greater than Z2, or Z1 is very much less than Z2, either one, or the difference between Z1 and Z2 is very large, alpha is almost 1. These two difference very large, alpha is almost 1. Three reflection and little transmission. Okay, so 0, very little reflection, right? Almost 100% transmission, whereas if its alpha is 1, it's mostly reflected, little transmission. Memorize this one. Any comment? One thing still not clear? Don't worry about Z1 minus Z2 lah. Usually it's written as Z2 minus Z1 lah. Right? Either way, it's still, you square it, it becomes positive. Intensity reflection coefficient alpha depends on difference between specific acoustic impedance of medium on each side of the boundary, depend on Z2 and Z1. Low impedance means large transmission and low reflection. High value means low transmission and high reflection. Okay, that's the summary for you lah. Low value alpha means large transmission, all will pass through, and low reflection. High value means low transmission and high reflection. Ultrasonic waves are reflected at boundary, right? Boundary between the two layers. This is the incident at the reflected intensity. Where there's a difference in acoustic impedance, Z of the materials on each side of the boundary, this difference is in Z is commonly referred to as impedance mismatch. Right? Afterward, during the break, try the worksheet lah, so that it give you a chance to try out the calculation involved. Right? What is Z? What is alpha? Difference in Z is commonly referred to as impedance mismatch. The greater the impedance mismatch, the greater the percentage of energy that will be reflected at the interface. Interface is the boundary lah, right? That's called the interface or boundary between one medium and another. Intensity reflection coefficient, air and fat. That means this is air and then enter your body lah. It's 100%. Alpha is 100%. So it's no use to. You can't study anything inside your body because 100% reflected. Idea is you want it to be enter the body. Fat and muscle is 1.8. Muscle and bone is 41%. Right? Large reflection at air tissue boundary, approximately 100%. Very little reflection at fat, muscle, including including fat and tissue. Yeah, almost the same Z. Very large reflection at tissue and bone boundary. Tissue and bone boundary, large reflection. So water, soft tissue, fat, and muscle is under here lah. Has approximately the same Z, very little reflection. This means that bone shows up well in ultrasound scan. Air tissue boundary, we need a coupling gel of the same impedance as the skin to ensure 100% transmission. Right? Ultrasound image of fetus in the womb, view at 12 weeks of pregnancy. For air tissue boundary, we need a coupling gel of the same impedance as the skin to ensure 100% transmission. Usually about 0.03% reflection. Right? We cannot just put a transducer on the surface of the body and then observe. Cannot. Because air tissue boundary, 100% reflection. So nothing enter, very little enter. So we cannot see anything inside the body. The poor, right? That's why we use a gel, right? Coupling gel. The poor match of impedance between air and tissue means the ultrasound cannot penetrate the lung, right? Lung got air and soft tissue. Right? Memorize this one. Explain the use of gel on the surface of skin during ultrasound diagnosis. Very little transmission of ultrasound at air skin boundary. Almost complete transmission at gel and skin boundary when wave travel in and out of the body. Right? Remember, the ultrasound have to enter the skin and have to get out from the body through the skin. Okay, we have look at reflection and transmission. Now we will look at attenuation or absorption. Right? Either the term absorption or attenuation, the same thing. A second factor that affects the intensity of ultrasound wave passing through a medium is absorption. As the wave travels through a medium, energy is absorbed by the medium. Right? That's the intensity, incident intensity. There's a transmitted intensity, and that is a medium. The medium will absorb the energy. Right? As the wave travels through a medium, energy is absorbed by the medium, and intensity of a parallel beam decreases exponentially. Right? Remember this parallel beam. When it absorbs, energy is absorbed by this medium, then the temperature of medium rises. So heating effect caused by ultrasound of suitable frequency is in fact used in physiotherapy to assist with the recovery from sprained joints. What is absorption coefficient? That's your medium. This is the incident intensity, I naught. This is the transmitted intensity after passing through the medium, I. Intensity of beam passing through medium is related to the incident intensity, I equals to I naught E minus mu X, where mu is a constant for the medium, right? Called the absorption coefficient. Unit is per meter, right? No unit lah, no unit for these two lah, because one is in meter, one is per meter, so no unit. Yeah? X is thickness of medium, right? Same as radioactivity formula, right? Except different symbol used as all. That one is in your syllabus, in the data sheet. Right? For air is quite large. For bone is also quite large. For water is very small. This coefficient is dependent on frequency of the ultrasound. Some value of ultrasound or frequency, right, in megahertz range. Absorption of ultrasound in air and bone is large. Right? You can see that. Large absorption coefficient. Right? This is a fraction transmitted. Just take I note down now. There's a power. The larger the value of mu, the smaller will be the percentage transmitted. This coefficient is dependent on the frequency of ultrasound. Right? Remember, the absorption coefficient dependent on frequency. Larger the value of mu, the smaller will be the percentage transmitted. Right? In this case, transmitted means passing through the medium. Right? This is for your info. Low frequency, high frequency. Okay, that's the fraction reflected. That's the fraction transmitted. Right? I don't think I will bother to derive for you lah. Intensity received back at surface I2 surface. Right? That's your surface or the skin, the air at the surface after two absorption. We are looking at this layer. It has to go into this layer, and then part of it is at the gel there. We usually consider 100% transmission. Then there's an absorption here. And when it's reflected, right, at this boundary, bone muscle boundary, then it is absorbed again. That's why it's two absorption coefficient. Right? Fraction absorbed. And this is right. If you are big puzzle, what does the symbol stands for? That's the fraction reflected.